Hello, my name is Mizanur Rahim. Today we will discuss about gravitation, basically two topics. It is a very short video, force of the gravitation and acceleration due to gravity and its variation. So now the universal law of gravitation, and all of you are so used to objects falling that you may not have thought why those objects fall. There was a person who thought about it. His name was a famous scientist. His name was Sir Isaac Newton. And he concluded that a force acts to pull objects straight down toward the center of the earth. Sir Isaac Newton put forward the universal law of gravitation in 1687 and used it to explain the observed motions of the planets and the moons. And what he realized on that day, it is known now as the universal law of gravitation. Gravity is the force that pulls objects each other. It is the force that keeps the moon orbiting around the earth. It is the force that keeps all the planets in our solar system orbiting around the sun. And it is the force that makes an apple fall toward ground. So what he stated, what Sir Isaac Newton stated, every particle of the matter in the universe attracts every other particle with a force that is directly proportional to the product of the masses of the particles and inversely proportional to the square of the distance between them. And this attraction force is known as the gravitational force, which is F equal to G m1 m2 by r square. G is the universal gravitational constant, which is the fixed value 6.67 into 10 to the power minus 11 Newton meter square per kg square. It is in SI unit. And M1 and M2 are the masses of the two bodies. R is the distance between them. And from this equation, it is clearly showing that gravitational force is directly proportional to the product of the masses of the particles, and it is inversely proportional to the square of the distance between them. Force of the gravity of the earth. Earlier we have discussed that gravitational force is directly proportional to the masses of the particles, and it is inversely proportional to the square of the distance between the masses. Gravity is the force that pulls objects each other. And now if this mass of the particle increases, what will happen? The force of the gravity will definitely increase. And the perfect example is in our solar system. For that reason, all the planets orbiting around the sun, because of the masses of sun is very much higher than other planets, and for that reason the planets are orbiting around sun. And if this distance increase, what will happen? If the distance increase, the force of gravity decreases, and its perfect application is all the space shuttles or Mangalyaan. It is little bit hard topic. And so what we learn, gravitational force is always attractive in nature. Gravitational force is independent of the nature of the intervening medium, and gravitational force is conservative in nature, and it is a central force, so it acts along the line of joining the center of the two interacting bodies, and it obeys inverse square law. So in this short video, now we will discuss about the acceleration due to gravity and its variation. And actually, gravity is the gravitational pull exerted by the earth, and the acceleration produced in the body due to the force of gravity is called as a acceleration due to gravity. It is denoted as g, and g is equal to the universal gravitational constant, which is capital G, and the mass of the earth, which is 5.97 into 10 to the 24 kg, and it is divided by the square of the radius of the earth, The radius of the Earth is 6.37 into 10 to the power 6 meter. So the acceleration due to gravity is equal to 9.81 meter per second square. So now we'll discuss about the variation of acceleration due to gravity. It is very interesting thing because acceleration of gravity vary on couple of things due to the change in altitude, due to the change in depth, and it's also depends on the rotation of the Earth. We'll come one by one. So now we'll discuss due to altitude. I'm giving you a schematic diagram. Suppose this is the Earth's surface, and is denoted as the height above the Earth's surface, and Re is the radius of the Earth. So the acceleration due to gravity at a height h above Earth's surface. It is we can calculate this thing from this simple equation Gh equal to g into 1 minus 2h by Re, where Re is the radius of the Earth, height h is the height above the Earth's surface. From this simple equation, we can say if the height increase from the Earth's surface, the acceleration due to gravity will definitely decrease. And it's perfect example. A person who is standing on Mount Everest, his acceleration due to gravity will much smaller than the person who is standing at Kolkata. So it's vary due to height. More the height will increase, more the acceleration due to gravity will decrease. Simple thing. So now we'll discuss this variation due to FD, and from this schematic diagram, uh, D D is the depth below the Earth's surface, and this is the Earth's surface, and D is the depth below the Earth's surface, and R of E is the radius of the Earth, and we can calculate the acceleration due to gravity at depth D below the Earth's surface from the simple equation G of D equal to G into 1 minus D by Re, and from this simple equation we can say the value of acceleration due to gravity decreases with the increase in depth from below the Earth's surface and becomes zero at the center of the Earth, because at the center of the Earth this d will be equal to the radius of the Earth, and this whole thing will be zero. So d of d is definitely zero because this product will be zero. And I can show you the variation of acceleration due to gravity from this line at graph. Suppose this is the center of the Earth, and at the center of the Earth, d will be equal to the radius of the Earth, and it will be 0. And above the center, till the Earth's surface, the gravitation will increase, and g will be directly proportional to the distance r. And after the Earth's surface, again this acceleration due to gravity will decrease, and it is inversely proportional to the square of the distance. G is inversely proportional to the 1 by r square. One of the most interesting part of this lesson, due to the rotation of the Earth about its axis, how the acceleration due to gravity vary. So this is the schematic diagram for the segment. Omega is the angular speed of rotation of the Earth about its axis. This is the pole region. This is the equator region. Now, if we have to calculate acceleration due to gravity at latitude lambda, then we can calculate it from this simple equation G of lambda equal to G minus Re omega square cos square lambda. We can calculate this acceleration due to gravity at pole at equator, because at equator this angle will be 0 degree. The value of acceleration due to gravity G of equator equal to G minus Re R of E omega square, because cos 0 degree is always 1, and this thing will be G minus radius of Earth and square of angular speed of rotation of the Earth. And at pole, we all know this angle will be 90 degree, lambda equal to 90 degree. So value of acceleration due to gravity G of pole is equal to G, because cos 90 degree is 0, and therefore this product will be 0. So G or G lambda will be equal to G. So therefore G of pole is equal to G. So from what we understand, the value of acceleration due to gravity increases from the equator to the pole due to rotation of Earth. And two more important thing we understand: if the Earth stops rotating about its axis, this omega will be zero. Therefore, there is will be a increase in acceleration due to gravity everywhere except poles, because this whole thing will be zero. G of lambda will be equal to G. And if there is an increase in angular speed of the Earth, means if there is an increase in omega, then except poles the value of G will decrease at all the places, because this subtraction result will be decreased due to the increase of omega. So thank you for your patience. Any questions?